Hey everybody, in this video, I'm going to be running through an example of an object that's rolling down an incline without slipping. This is a continuation of the previous video where I introduced you to both types of rolling motion, and in this one, we're going to be using a little bit of both, although most of this problem is rolling without slipping. So looking at this, we've got a solid disk of mass m, radius r, and moment of inertia I equals 1/2 mr squared. That's nice, they give it to us. And it's rolling from rest, that's important, from the top of an incline, height h, that's also pretty nice, and it has an angle theta. It also gives us the length x of the incline, which is interesting, so we may need that later. The coefficient of friction with the incline we're claiming is high enough that the object is going to roll without slipping, and that information is huge. That tells us, based on the last video, that if the object's rolling without slipping, that gives us two equations that we are now permitted to use. Firstly, over here, it tells us that the linear velocity of the object has to be equal to the radius of the object times its angular velocity. Similarly, with acceleration, the linear acceleration has got to equal the radius of the object times the angular acceleration of the object. That's important because that helps us convert certain quantities from their rotational version to their linear version without any trouble. With part A here, we're being asked to determine the linear velocity of the object when it reaches the bottom of the incline. Now, the way that this question is worded immediately rings off bells that this is going to be conservation of energy. Why? Well, a couple of things. First off, it is rolling without slipping. This means that friction isn't really doing any work to drain energy out of the system. Because of this, we know that whatever mechanical energy we have at the start is going to equal whatever mechanical energy we have at the final case. That should be final. Now, another thing that rings off bells is that we do have the initial height that the object starts with and the initial speed that it starts with. So we can figure out the initial potential energy of the system. And then because we're trying to figure out the velocity of the object when it reaches the bottom of the incline, that's the final nail in the coffin for any other strategy that could be used here. That is a total energy problem if I've ever seen one. So looking at the initial energy of the system over here, we're really only going to have gravitational potential energy. And with our given quantities, that's easy enough to calculate. It would be just the mass of the object times the acceleration due to gravity times whatever height the object starts with. Now, in the final case, we have two different things because now potential energy has been completely used up. It's going to be converted into both translational kinetic energy and rotational kinetic energy. Writing those equations out, we would have 1/2 mv squared, the usual culprit, and then our new kinetic energy equation, which is 1/2 times the moment of inertia of the object times the angular velocity squared. Putting these together then to try and solve for the linear velocity, noting that this is our goal here, this little v, we're going to start with our initial potential energy, so mgh, and that's going to equal 1/2 times the mass of the object times the final velocity squared. We can just leave it in that form. It doesn't seem too troublesome. But then for the kinetic energy, the rotational kinetic energy over here, we can substitute some stuff out to get it more in a form that's in agreement with this linear velocity here. For instance, we can go ahead and substitute in the rotational inertia of the object. That's 1/2 mr squared. And then the angular velocity over here, since this conversion is available to us, we can state that the angular velocity is the linear velocity divided by the radius of the object, r. So we can multiply by v squared over r squared over here. Now this opens up a couple of cancellations for us. Every single term in this equation has an m, so we can go ahead and splinky those out. And then finally, we've got an r squared on the top and an r squared on the bottom that's reared its head, so we can get rid of those too. Our final result then is going to look something like this. GH equals 1/2 times 1 plus 1/2, that's pulling out a 1/2 and a v squared from both of these terms, times v squared, which both terms have. Now, if we simplify things a little bit here, we would find that the final velocity here is going to equal the square root of 4/3 times the acceleration due to gravity times the height that it starts at. And that is the first part done. Now, the second part here has us determine the linear acceleration of the object on the incline. Now for this, since we have the final velocity available to us now, and we have the initial velocity available to us now, let's start putting out some of our information here, and it's going to become very clear very quickly what we need to do. Our initial velocity is 0 meters per second. Our final velocity, we have the expression for now. Let's what we had before. And something that is helpful is that we do know the length that the object travels through, or the distance that the object travels through. It's this length x right here. Knowing that, we've got a displacement, which is this distance x. And so if we're looking for the acceleration of the object, then we have 3 pieces of kinematic information available to us and 1 kinematic information that we're trying to solve for. From that alone, this can be treated like a kinematics problem. So over here, the most appropriate equation for it is going to be vf squared equals v naught squared plus 2a times the displacement. And knowing that this is 0, we can get rid of that term. So the linear acceleration is going to equal vf squared divided by 2 times the displacement. So simplifying things a little bit then, we would get that the acceleration equals 2/3 times the acceleration due to gravity times h divided by the displacement it travels through a little bit of algebra. So that's nice. And now in part C, we're looking for the force of friction acting on the object as it rolls down the incline. Now with this one, we have an acceleration that's available to us now. So if we're looking for a force, might we consider using Newton's second law for this? Now for that, it's probably best if we make a free body diagram over here. So if we're treating the center of the object as where the axle or where the center of the disc is, we've got a force due to gravity going straight down. And because it's on an incline, we can split up its components into the parallel and perpendicular direction like this, noting that this angle right here on our triangle is the angle theta. Now going up away from the surface is the normal force up here. And then there is friction still in the system. It's just not doing any work on the system. And that friction force is opposing the object on the incline. Now, why is it opposing and not going with? Well, again, remember that this object is translating down the incline, and friction consistently goes against the motion of the object. Another reason is, well, if you're thinking about how this object is rotating, if the object is rotating this way, like that, then friction is the thing that's causing it to rotate that way, that's applying the torque that's causing it to rotate in this clockwise direction. So with that in mind, let's put together Newton's second law for this. So the net force acting on this object is equal to the mass of the object times that acceleration we solved for in the previous part. And in the direction of motion, which is down the incline this way, we've got the parallel force due to gravity. So that would be mg times the sine of the angle, and then going against is that force of friction that we're trying to solve for. And all of that is going to equal the mass of the object times this acceleration we got in the previous part. So 2/3 gh over x. Now rearranging everything, we're going to end up with the force of friction equaling the mass times the acceleration due to gravity times the sine of theta minus 2/3 h over x. And yes, this can be simplified a little bit by noting that with our right triangle here, x is the hypotenuse, h is the opposite, and sine of theta, notably, is the opposite divided by the hypotenuse, so h over x. So this h of x term right here can be simplified to sine of theta. That means that whatever's left is going to be 1/3 sine theta, and so our final expression could be interpreted as 1/3 mg times sine of theta. But I'm going to leave it in this form and move on. So now this last part here is if the coefficient of friction mu is small enough that the object slips as it rolls down the incline. If that's the case, we're now being asked to figure out the acceleration of the object as it rolls down the incline. Now, again, for this case, really the main thing that changes is that now we know a coefficient of friction that's small enough to cause it to slip. Since that's happening, all we can really use is the coefficient, or is the force due to friction formula, which is that force of friction is equal to mu Fn. Now that that's available to us, it's very clear that we should be using Newton's second law again. Now, since the acceleration is our goal here, we really just need to expand out this sum of forces. So again, we're going to start with the force due to gravity times sine of theta, which is the parallel component pulling it down the incline. And going against that is the force due to friction, which now we can expand out as mu times the normal force. And that's all equal to mass times acceleration. Now the normal force itself is the other component of gravity that we solved for earlier. So that would be mg times cosine of theta. So expanding that out even further, we would end up with something like mg sine of theta minus mu mg cosine of theta, and all that equals ma. And again, every term now has an m in it, so we can get rid of all of those. And from that, we effectively have solved for the acceleration, because there's nothing else on that side. So the acceleration of this object that's slipping down the incline is going to be g times sine of theta minus mu cosine of theta, and that is our new acceleration, whatever that may be. And so in doing all of that, we end up with our final set of solutions over here. So this is one of many examples in which you could apply rotational motion to an object on an inclined plane. And it's really just worth noting just the sheer range of formulas and equations and concepts that you have to apply to an object that's just rolling down an incline. So it's really important here to really highlight every single piece of information that's available to you in this problem, and also to remember what conditions you're allowed to apply, whether the object is rolling without slipping or rolling with slipping. You really have to extract every little piece of information and every equation that's available to you to solve one of these problems. They can get very complicated, and so it's a true test of all the physics that you know up to this point. So in the next video, I'm going to cover another example that applies some different techniques, and from that point on, hopefully you're prepared to approach any other rolling motion problem. So I hope this video helped, and I will catch you on the next one. Peace.